Hello. So in this video, we'll be talking about how Lumerical can be used to perform a system level analysis. We'll be continuing with the example of waveguide based Lidars. So just to recall, we basically have an array of waveguides, something like which is shown here, and which scatter light and basically form a beam. And by controlling the relative phases of light which is going into this waveguide, we can do beam steering into different directions. In the last couple of videos, we had seen how um, numerical mode can be used to uh, study the mode inside the waveguide and study directional couplers. And then we had talked about how FDTD can be used to look at far fields of a single antenna as well as array of antennas and basically look at how beam steering can be performed by and how the beam will actually look like in the far field. Uh, Now interconnect can be used to simulate the whole system. So for a LiDAR, this system will consist of a source, a modulator, a series of modulators rather, waveguides, and of course an antenna array, basically. Um, all these elements have properties like, for example, waveguides will have something like insertion loss. Even the modulator will have insertion losses. Also, the modulator will have parameters uh, like different coefficients will determine how much the phase will change for a particular length of propagation when we apply a certain amount of voltage, all those things. So all this can be integrated together into a single platform, which is basically interconnect. So before we actually look at uh, the LiDAR example, I just want to briefly show you uh, the overall layout or how it actually looks like interconnect and what just a brief description of the building blocks which we'll be using. So first of all, you have this library over here, which you can see, which is called the element library, and you can basically choose a bunch of sources. Like for example, in optical, you can choose your lasers and what kind of laser you want. You can choose modulators, and you have pulse generators, sequence generators, you have waveguides, etc. I mean, yeah, you can explore all this according to your application. So here I am basically just showing uh, the components which we'll be needing. And so the first thing is, of course, our laser source. Then you have um, a waveguide coupler. So you basically send in light into one of the ports, and then uh, it's basically a 50-50 splitter, or you can choose it to be, whatever splitting ratio you want it to be. And then light is split into two components. Then one of these components will actually go to a waveguide, and then from this waveguide, it will go to a phased array. And how that phased array can be described, I'll just uh, describe in shortly. The second beam, which it actually goes through an optical modulator, and it's important that the beams are all coming out from a single input because you want to keep some kind of phase relationship, and that's how it is typically also done in an experiment. And this optical modulator can be applied an electrical voltage. So there is this pin which you can see here, which is the modulation pin, and we will see in the later example now this can be connected to a actual voltage. And at the output port, then you will end up with a modulated signal, and then similar to this C1 here, you can have C2 and so on. Then typically, basically, if you had more elements below, then you could actually draw a signal out from here and then modulate it more and so on. Uh, Another feature of interconnect is that you can actually put in a scripted element, and a scripted element is an element which can be defined by a script basically, and you can create or define its ports. So I can just show you. So here you can basically define different variables or different ports. For example, in this you can define your different ports, and and then the results, this will basically show what will be at the output. And the simulation has a bunch of scripts which can be written and which will be executed at different points of time. So the setup script basically uh, yeah, defines your variables and parameters, and the ready script defines when is the element activated, like so for example, in our case, the element will be activated when all the input signals have some valid data at the input port, and then go script will basically be executed when all this data has been there, and it does certain kind of processing which we want, and then sends it into the output variables. And the wrap-up script actually does the same things which are described in the Go script for different values of time. So it will produce an array with respect to time, because we'll be varying parameters with time. So now let's go to the actual layout for Lidar. So as I described, so this is how it looks like. So maybe I'll just reduce this a little bit. Mm, Okay. So we see that this is the source, and then you have yeah, here a bunch of optical modulators, and the modulation signal is given somewhere below here. I can show you that. So here, which is basically a ramp, and you can click on this to see its properties. And for example, you can see how the slope is. So something like here. And what we are doing is we are basically taking this signal and then we are splitting it up using a splitter here into different outputs. And each of this is then sent to the modulator, the modulation port of the optical modulators. And then this is sent to different waveguide couplers, and then it's sent to the waveguide and then to the scripted array element, which in our case is basically our um, phased array. So now this phased array uses some of the data which was available after the FDTD simulations, which we did last time. And basically what that was how the far field looked like, the electrical distribution, the electromagnetic field distribution of a single antenna as well as an array of antennas, and how the beam spot shifts with respect to frequency as well as theta and phi. And uh, so in this for the interconnect, we can basically define our Go scripts, which will determine the direction of the beam width based on the the phase of the input signal which is coming in. And as we had seen in the first video, that by giving a appropriate uniform phase shift to all the different elements of an antenna, you can choose the direction of your beam steering. Um, so at the output, then we have the uh, direction vectors, which are basically given by ux and uy, which are the x and y component of your uh, position vector of your beam spot. And then you also have the beam widths, which are given by ux and uy. And then, of course, you can actually also directly look at the values of theta and phi. So uh, you can, for example, do this simulation where I've already done this and we have results for that. So let's look at, for example, how the theta and phi values change with respect to time. So on the x-axis, we have uh, time in nanoseconds. So, sorry, time in seconds. And here we see that how theta and phi are changing with time, and we can basically see that the value of phi can be tuned from -60 to +60 almost, while the value of theta goes from 40 to, yeah, about slightly less than 20, about 18 degrees, and goes back up from there. So uh, we can do all sorts of interesting things using interconnect. So one, for example, in this in the optical modulator properties, you can actually define, depending on the optical modulator you are using, you can actually um, define your coefficients which determine how the phase changes. For example, the phase coefficient here. So this can be changed according to, whatever kind of optical modulators you are using. So that's really awesome. Plus, you can also include things like, insertion loss, absorption coefficients, and even inside a waveguide coupler, for example, you can see how the splitting ratio is. Yeah, here you can, for example, define your insertion loss. This is like the coupling coefficient. So yeah, so basically you can play with a lot of things, and the best part is interconnect allows you to visualize your actual sort of system setup and giving you and it allows you to integrate results obtained from other modules like Lumerical, mood solutions, and FDTD, and play with all of that together and visualize the end results. So hope you like this video, and yeah, for details you can always look at Lumerical knowledge base, which has a lot of information on all these things. Okay, hope you learned something nice from this, and thanks a lot. See you until next time.